Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hi. Today in this subject, which is Introduction to Reactor System, my group, which is Group 6, represent a topic which is Concept of Catalytic, Multifunctional and Microreactors. My name is Muhammad Fawaz bin Mazlan and my metric number is 1192451. My group members consist of 5 students, including me. The others are Ilham, Ahmed Ikram, Hanis Hashimi and Wan Muhammad Zulhilmi. Without further ado, let's go to the presentation. Catalytic reactor are defined as a device that encloses the reaction space and which houses the catalyst and reacting media. So, it is a container to which reactants are fed and products removed that provides for the control of reaction condition. So, in short, catalytic reactor is a reactor that contains catalyst. Catalytic reactors can be classified using 4 aspects. The first aspect is the size. The second one is the methods of charging or discharging, which is batch or steady state flow. Next, the motion of particles with respect to each other are also the aspect to classify the reactors. And the last aspect is the fluid flow type, which is the tubular reactor or mixed fluid reactor. When we said about catalytic reactors, of course, it has catalyst and the catalyst has its own properties and characterization. So the first characterization, which is the surface of catalyst. Catalyst surfaces should be carefully prepared and pre-treated so that it's free from contaminants and its activity won't be affected. Next, the support effect. Support effect can be avoided by studying reactions on single crystals of the active catalytic phase. For example, the decomposition of metal carbonates on supports. Next, the next characterization is the surface structure. The surface of structure of the catalyst is important in case of if the reaction is structure sensitive reactions. Next, the metal dispersion. The metal dispersion in the catalytic reactors can be measured using proven and or standard methods. And the last properties, which is the methods of preparation and characterization. The methods of preparation and characterization should be recorded carefully so it can be reported. Next, I will talk about the physical and mechanical properties of catalysts. The first property is density, which can be defined of mass per unit volume of the catalyst. Next properties is pore volume, which is defined as the volume of pores per unit mass. Next, which is pore size and size distribution, which is the average size or diameter of a catalyst and its size distribution. Next, the surface area. So the surface area of pores for the catalyst. Next, the properties is catalyst particle size, which defined as the diameter or length of pellets or extrudates or hole size, which is pitch of the monolith. Next, the crushing strength, which can be defined as the force necessary to crush the catalyst particle in axial or radial direction. And the last properties, which is the attrition, which is the percentage loss per time of the catalyst due to tumbling. Okay, for my last slide, this is on heterogeneous catalytic reactors design goal. So the first design goals for heterogeneous catalytic reactors, which is rapid and intimate contact between catalyst and reactants. So we want the collision between the catalyst and reactants to be maximum so that we can produce maximum activity. And the second goals, which is to ease of separation of products from catalyst so that the product can be successfully extracted. Okay, there are four types of heterogeneous catalytic reactors, which is fluidized, fluidized bed reactor, slurry reactor, packed bed reactor, and catalyst recycle reactor. The brief introduction about the reactor can be read in the note given on this slide. Thank you.
I'm Muhammad Amikram bin Yusof, 1192463. I am from group 6. So, for my part, I am going to explain the characteristic of heterogeneous supported catalyst. So there is three characteristics, which is surface area, loading, and dispersion. So for surface area, as we can see on the slide, the surface area is the limiting factor for the heterogeneous supported catalyst. Why? Why surface area is one of the limiting factor? Because once the surface completely saturated with reactant molecules, the reaction cannot proceed until there is available space for a new reactant molecule to absorb or attach to. So for the second characteristic, which is loading, the metal particle size is a critical structural parameter that determines the catalytic activity of supported metal catalyst. Hence, smaller particles tend to have more active site compared to larger metallic particles. So for the third characteristic, which is dispersion, common catalysts contain very small particles, typically in nanometer range, which are dispersed onto a high surface area of the catalyst. So now we will continue with the absorption and reaction at solid surface. So for the physiabsorption resembles the condensation of gases like N2 gas to liquids depend on the weak van der Waals attraction for any surface. There is no chemical specified in physiabsorption. Any gas tending to absorb on any solid if temperature sufficiently low or pressure of gas sufficiently high. So it's useful on measuring gross surface area. So for the chemisorption, gas are held to a solid surface by specific chemical force for certain surface and gas usually occur at higher temperature. It is lower compared than physisorption. Chemisorption is useful in measuring catalytically active sites. As on the slide, we can see the energy that release when absorption happens. The chemisorption has higher energy release when absorption happens. It indicates that the chemisorption is stronger than the physisorption. So for the next part is physisorption versus chemisorption on magnesium oxide. Magnesium oxide can absorb carbon dioxide below the temperature 200 degrees Celsius. Magnesium oxide is one of the most promising absorbent for carbon dioxide. When magnesium absorbs CO2, carbon dioxide, it is physisorption instead of chemisorption. This is because it happens in the low temperature. So when magnesium oxide react with sulfide or sulfate, it is MgO can absorb sulfide or sulfate at the specific temperature, which explain why the process is the chemisorption. So for the next, we will measure the concentration on heterogeneous reaction kinetic. So there is two category, which is fluid concentration and surface concentration. So the fluid concentration, which is traditionally reported as pressure, which is store, ATM or bar. We will use the ideal gas assumption, which is P equal to CRT. Instead of PV and RT, we use P equal to CRT because we want to measure the concentration. So for the next category, which is surface concentration, if we want to calculate the coverage per unit area, we will use the formula N equal to moles per area. The N is equal to coverage. So for the next, if we want the maximum coverage called monolayer, one monolayer max is approximately 10 power of 15 molecule per centimeter square. So for the formula for the fractional coverage, which is theta J equal to coverage per unit area per maximum coverage called monolayer. The the ratio for the theta j is between 0 to 1. So for the last topic on my part is the catalyst analysis and the characterization. So on the table, we can see that the method is depend on the characteristic of the catalyst. If the catalyst has the surface area, pore volume, and size characteristic, we will use the method N2 absorption, desorption, surface area analyzer. If the catalyst has the characteristic phases present and crystallinity, we will use the method X-ray powder diffraction TG/dTA for precursor, and so on. So if the catalyst has the morphological characteristic, we will use the method which is the scanning electron microscopy. So we will end my part with the rate of the catalytic reaction formula. So take your time to see and read the slide. Okay, that's all for me. Thank you.
So, Bismillahirrahmanirrahim. My name is Muhammad Ilham, metric number 1192450. So, I will be explaining some example of catalytic reactor. So first we have here is BET surface analyzer. As we know, as we mentioned before, surface area, pore volume, and size is one of the catalyst characteristic. So how we want to determine this characteristic? So we can use the method of nitrogen gases absorption desorption surface area analyzer, also known as BET, that applying Lamoy concept. So what is BET? If you want to know, BET is referred to the Brunel Emmett-Taylor theory that aims to explain the physical absorption of gas molecule on a solid surface. It is a very important analysis technique for the measurement of the specific surface area. These observations are very often referred to a physical absorption or physisorptions. So the next example for catalytic reactor is chemisorption analyzer. As we know before, dispersion, metal surface area, and metal particle size is one of the catalyst characteristic that we mentioned before. So how we want to determine this characteristic? So we can determine it by using the method of chemisorption. Also, we can use the TEM. So if you want to know what is the meaning of the chemisorption analyzer, what is the function of chemisorption analyzer. So chemisorption analyzer is a measurement technique that are very useful for evaluating physical and chemical properties of material that are critical for process or even for the reaction performance. Primarily, as we know, chemisorption is also used to evaluate the number of available active site to increase the rate of the catalyst or to increase the rate of the chemical reaction. Okay, as I mentioned before, that we know that BET is useful for measurement of the surface area of the catalyst. So here is the example how we analyze the BET. So the BET analysis is performed by plotting the X overview 1 minus x versus the x, where x is p over p prime, which is p prime is equal to 1 bar, and v is referred as the volume of the nitrogen adsorbed per gram of MOF at standard temperature. As I mentioned before, that we in this reactor we will use nitrogen gases. So as we can see at the graph, the linear graph that we have two lines. So the lines refer as the reaction as the relative pressure is increased. Also the volume absorbent will also increase. This is the example of the surface area that we can calculate, that we can plot using the BET. Okay, on the previous slide, we have discussed how to calculate, how to plot the surface area. And for this time, I will explain on how we can calculate or how we can plot the pore size distribution. So, pore size distribution can be calculated or can be can be plot by using BGH method. So, what is BGH method? What is BGH? BGH refer for what? BGH method is Barrett, Joyner, and Halinda. This is three names that refer to the BGH. It is a procedure for calculating pore size distribution from experimental isotherm using the Kelvin model of pore filling. It's applied only to the mesopore and small micropore size range. BGH calculation is very useful for plotting a pore size distribution graph. As you can see here at the bottom of the graph, this is the formula used to calculate the pore size distribution. So as we can see at the graph, we can see two different lines that we obtain. So the graph is between pore diameter versus the pore volume. So by uh, doing this graph or plotting this graph, you can observe the pore size distribution. Okay, next, let's discuss about the classification of reactor. Okay, the classification of reactor is divided into four groups, which is we have the size, we have the motion of catalyst particle relative to each other, we have the method of charging and discharging, and we have the fluid flow. So let's discuss one by one. Okay, first we have the size. Okay, which instrument or which apparatus or technology that suitable to measure the size. So we have, for example, we have the reactor, laboratory reactor, we have bench scale, we have pilot scale, we have plant scale. For the example, there are example featuring this apparatus is it have a 0.5 centimeter diameter tubular microreactor that can calculate 0.1 until 1 gram of catalyst. They also have 7.5 centimeter diameter times 6 until 10 meter long of tubular reactor. This is very suitable to measure the size of the catalyst. The next classification is motion of catalyst particle relative to each other. The example of technology that's suitable for this classification is it is fixed relative motion. So fixed relative motion is a tubular fixed solid, also known as fixed bed. So fixed bed I will be explaining later. So fixed bed is divided into two categories, which is fluidized bed and slurry bubble column. And the third class is method of charging and discharging. Okay, method of discharging and charging. So which instrument that's suitable? It is a batch flow and steady state. The featuring this apparatus is it have stirred liquid and solid. For example, tubular, fixed catalyst bed, and we have slurry, mixed fluid, and mixed solid. That's for the example that for the method of charging and discharging. And lastly, we have the fluid flows, which is the suitable instrument that we can use is tubular, plug flow mix and fluid flow. Plug flow, okay, we can use the tubular plug flow and mixed plug flow, fluid flow. For example, we have turbulent gas in tubular fixed bed as a slurry reactor that we use to stir. Okay, that's all for the classification of reactor. Okay, for the last part, I will explain about the laboratory and bench scale catalytic reactor. As I mentioned before, the classification uh, I have tell you guys about the example of the reactor that has been used to determine some part of the classification. So for this slide, I will explain generally about the laboratory and bench scale catalytic reactor. Okay, we have fixed bed tubular. Second, we have stirred gas, which fixed bed, and third, we have fixed bed transient gas flow. Fourth, we have stirred liquid or gas, which is stirred catalyst, and lastly, we have fluid bed. Okay, first I will explain about the fixed bed tubular. Okay, what is fixed bed tubular? A fixed bed reactor tubular is a fixed bed reactor that is a cylindrical tube filled with a catalyst pellets with reactant flowing through the bed and being converted into product. The flow of fixed bed reactor is typically downward, which is a packed bed reactor. So what about the class? What about the class? Okay, which is it is categorized as laboratory, differential, or integral bench scale integral. So what is the featuring for this item, which is it also have 0.5 centimeter diameter tubular microreactor, which is 0.1 gram and 0.1 until 1 gram of catalyst, and we also have 7.5 centimeter diameter and 6 until 10 meter long tubular reactor. Second, a stir gas phase bed, which is stir gas phase bed is also classified as a stir batch, which is bubble slurry. The featuring of this item is it have a tubular feed solid, which is phase bed, as I mentioned before. It have fluidized bed. It has slurry bubble column. Okay, what is fluidized bed? Okay, fluidized bed reactor offer a much higher efficiency in heat exchange compared to the fixed bed and better temperature control due to the turbulent gas flow and rapid circulations. And lastly, next we have fixed bed transparent glass gas flow. Okay, it is classified as a gas flow known as TPD or TPSR, and also it also classified as a radio tracer exchange MS or transient response and frequency response. Okay, featuring for this uh, apparatus is it have a microreactor that can detect 0.1 until 1 gram of catalyst, which is the glass or metal or uh, or etc. Okay, next we have stirred liquid gas or stirred catalyst. Okay, what is stirred gas? Okay, stirred reactors are more commonly used for batch reaction without any flow through the reactor and are often used for solid or liquid or solid-liquid gas reactions, in which the solid catalyst is suspended in powder form in a liquid which is maybe inert or one of the reactant. Okay, for the classify, we have some example here. We have stir batch recycle, Bertie, and Carberry. The featuring for this equipment, it have a batch scale 2 until 50 gram of catalyst, until 1 until 200 atmosphere glass or metal, heterogeneous or homogeneous catalyst. And lastly, we have fluid bed, which is, as I mentioned before, what is a fluid bed? Okay, class is categorized as laboratory bench scale, transport bench laboratory reactor. It also is bench scale transport, recirculating transport. For the featuring for this apparatus, it is a turbulent gas in tubular feedback slurry reactor with mechanical steering. Okay, that's all from me for presenting today. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Hanis Hashimi bin Shamsul Bahri, metric number 1192465. Today I will explain 7 criteria for selection of catalytic reactor. First, it must satisfy purpose of measurement. To achieve that, we simulate the process regularly. Second, avoid catalyst deactivation where possible. If not, decide either it fast or slow. Catalyst got deactivate where it decay either slow or fast. If it's slow, we use CSR or differential reactor, and if it's fast, we require the use of transient or transport reactor. Third, avoid inter and intraparticle heat and mass transport limitation. To meet this criteria, we operate at low conversion and or use CSR or differential reactors. Fourth, minimize the temperature and concentration gradient. This is because gradient cause activity and selectivity disguise. If possible, use CSR or differential reactor. Fifth, maintain the ideal flow patterns. To maintain them, avoid gas or liquid holdup in multi-phase reaction system. 6. Maximize the accuracy of concentration and temperature measurement. To achieve this criteria, we must use the right analytical methods and sensitive probes. 7. Minimize construction and operating costs. This can be achieved if we select the least expensive reactor that will satisfy the other criteria. Next, I will explain the application of catalyst, which is industrial application and environmental application. For industrial catalysis, first, catalysis is used for a better process economy and productivity. Catalysis can help the reaction occurs faster Thus, we can save more time and save the cost. Second, reducing waste. The catalysis can help improving the selectivity toward desired product, thus less raw materials required and less unwanted wasted. Third, producing catalysis-dependent product. We can produce certain product that only can be made with catalysis. Fourth, better control of process. The catalysis can provide the alternative pathway of reaction that can reduce the energy required for reaction to occur. Fifth, encouraging the advancement of new technologies. Nowadays, the industry more focused on improving existing polymers, pharmaceuticals, biologically derived products, and we can see many products be commercialized day after day. Last but not least, the example of industry that employ the catalysis in their sector is petroleum, energy, fine chemicals, and etc. because they are highly demanded either domestically or globally. Next, we move on to environmental application. First, the catalysis is used in pollution control. It can help reduce the waste and change or convert the composition of emission by the industrial factories. Second, the catalysis can help to reduce the pollution. For example, it can help to convert the harmful gas to non-harmful gas. It can also be used in water treatment for wastewater, drinking water, or groundwater. Third, the catalysis makes things greener. Catalysis is a way to save energy, and applying catalysis on a grand scale could save the world a lot of energy. Multifunctional reactors are a single piece of equipment in which, beside the reaction, other functions are carried out simultaneously. The other function can be a heat, mass, or momentum transfer operation, and even another reaction. As we can see from the diagram below shows the example of multifunctional reactor. Apart from the reaction that occur in the reactor, there is also the cooling feature that occurs simultaneously with the reaction to help the reaction occurs in the optimum condition.
So next, my name is Wan Muhammad Zuhilmi. My matrix number is 1192481. So I will explain about microreactor. What is microreactor? Microreactor is a device in which chemical reaction take place in a confinement with typical lateral dimension below 1 mm. The most typical form of such confinement are microchannel. So this is the picture that explaining about the microchannel. So next, the explanation of the microreactor. Catalytic process in microreactor are related with uniform channel structure and factor catalyst support. Term microreactor technology is used to describe the continuous processing of reaction. It is different with batch reactor and it happens within defined channel dimension less than 1 mm. Major benefit of conducting reaction under flow condition is the rapid early stage reaction optimization and direct scale up. It can be achieved by increasing the running time of the reactor, is a scaling up, and running numerous reactors simultaneously is a numbering up. This benefit leads to reaction miniaturization and promotes the theory of process intensification, as well as reducing the financial burden associated with scaling up a process. Miniaturization is designed in a small size. It can result in getting test result faster since small volume requires. Microreactors made from advanced structure and materials consist of narrow channel formed from materials such as silicon, glass, stainless steel, ceramic, or polymers. Due to the small size of microreactor, they must be made with high precision. These channels are made using such techniques as lithography, electrical discharge machinery, or laser micromachining. So next, we move on to monolith catalyst. What is a monolith? Monolith is a substrate that supports a catalyst. Most of microreactors use monoliths as catalyst support. Monoliths are made of a ceramic that contain a large proportion of synthetic cordiarite, which has a low coefficient of thermal expansion. The properties of monolith is it has thousands of parallel channels or holes. It is a many thin walls and the structure is honeycomb. Next is a microprocess plant. What is microprocess plant? Microprocess plant is one of the study of microprocess engineering. It is divided by four. It is a process engineering, microsystem engineering, chemistry and catalysis, and lastly microprocess analytical. Okay, I will explain about the process engineering. First, design of the microreactor. The choice of design and construction material for a microreactor depends on the intended application. Next, control system. In microreactor, it is important to control the time, pressure, and temperature. Then, flow pattern. Microreactor use a continuous processing technology because it has an input and output. It enables tight control of product specification. And lastly, simulation and optimization. When microreactors are integrated with chemical analysis, such as optical spectroscopy, they become powerful tools for determining chemical kinetics and optimal conditions for chemical reaction. Next, chemistry and catalysis process. So first, raw material. We can use glycosylation as the example of the raw material. Reaction kinetics. The latter feature becomes particularly important when chemical transformation involve highly reactive intermediate. Its large exotherms can lead to thermal runaway with potentially catastrophic consequences. Then, reaction pathway and mechanism. Microfabricate system consisting of multiple sub-millimeter channels in which fluid flow continuously and chemical reactions take place. Lastly, catalyst characterization. Microreactors usually use heterogeneous catalysts. Third is microsystem engineering. Basic material is silicon, glass, stainless steel, and polymer. Microprocess component, small catalyst particle size and reactor geometry eliminate mass and thermal gradient both internal and external to the catalyst particles. And lastly, microprocess analytical. We can use microanalyzer such as GC, LC, MS, TOF, and a specific technique for monitoring species concentration. We can use fluorescence, electrochemical, NMR, optical absorption such as UVs and IR. So this is some advantage of microreactors and monoliths. First, high surface to volume area is enhanced mass and heat transfer. Next is high volumetry productivity. It's a laminar flow condition. It is low pressure drop. Then it's a controllable RTD and bed mixins and its high volumetric productivity, and then its a low manufacturing and operating cost, and it increased safety due to small amount of material, and lastly, it's a scale up in a parallel. Lastly, the potential problem, which is a disadvantage of microreactor. First, short residence time require fast reaction, and then fast reaction require very active catalysts that are stable. Then catalyst deactivation and frequent reactor repacking or reactivation, fouling and clogging of channel, leaks between channel, malfunctioning of distributors, reliability for long time on stream, and lastly, the structural issues. So far, there are only two major commercial uses of microchannel system, which is monolith. First is automotive catalytic converter, which is a major success. And then selective catalytic reduction is NH3 to SCR of power plants and OS. So that's all from me. Thank you.